In this section, we'll look at longest common extensions, a data structure problem that at first sight doesn't really tie into suffix trees much, but we'll see right after that suffix trees are the key to solving this problem efficiently. So let's have a look at this, at the definition, what this problem is about. And I'll point out that, again, as we've just seen in generalized suffix trees in the previous section, where we try to find the longest common substring of a set of texts, suffix trees are good for identifying longest common prefixes of suffixes. So the longest common extension problem, nothing to do with suffix trees for starters. We're just given a text, and you can look at the text, you can pre-process the text, and afterwards I'll ask you queries of the form. Here's two positions, I and j. Maybe a picture again. Here's your text. I can ask for a position I and j. What is the longest, what's the largest amount of characters you can read from both positions to the right, and you see the same substring? So you read to the right, there's a certain part that occurs at both positions. And so in formulas, that's what's written down here. The longest common extension is the length of this green part. So it's the biggest L, so that if you read the substring starting at I, respectively at j, you get the same string. And this maximum here just means we want to capture the longest such L, which means the next character differs necessarily. Again, it's useful that we terminate our text with this dollar symbol, so we never run out of bounds in this definition. So this is always well defined. Now, we'll see in a second how we can implement this data structure. So this is, if you like this again, I shouldn't say data structure. This is an abstract data type. It's just telling you what the operations are. So maybe fix the slides here. Remember from Unit 2 back then, a data structure tells you specifically how to do things, whereas this is really just telling you what to do. So it's an abstract data type in that sense, and we'll see different implementations of this abstract data type on the next slide. A key idea is that the suffix tree somehow seems well suited to support this. Simply because longest common extensions are just a renaming of a concept we've used before. So let's unwrap this a little bit. If we want the longest common extension of two positions I and j, we can also look at the suffixes that started those positions. And look at their longest common prefix. So that's just a different name. I'm introducing this abbreviation LCP already here, because it will pop up later again and will be another big player in a sense. So these two things are the same things. They're just named differently, but they're really by definition the same. And also, if you have two suffixes, then in a suffix tree, there's two leaves that correspond to these starting indices, I and j. And now, something that might not be completely obvious at first sight is if you find the lowest common ancestor, that tells you what the longest common prefix is. So let's do an example in our tree here. If we want the longest common prefix of T5 and T1, we find the leaves for 5 and 1. And now lowest common ancestor just means you walk up the tree to the root from both, and these paths at some point join for the first time. So that's this node in this case. That's the LCA of leaf 5 and 1. And so what the rest of the statement says, if you look at the string depth, the length of the path from the root to this lowest common ancestor, that's the same as the longest common prefix. Why? Well, these are two suffixes in a suffix tree. So if you read the path from the root to the leaf, you get the suffix back. And they share this first part. So whatever you read on this shared path down to the lowest common ancestor has to be the same. And also at the next position, they differ. Otherwise, they would continue on the same path. Okay? So at first sight, this looks a little magic and maybe confusing, all these acronyms with L's. If you unwrap it on an example, it's really nothing deep. It's just an observation taken from how suffix trees are defined. Okay, so here's that statement in short again, and I put a box around it because we'll revisit this a few units down the road. But I think I have a copy of the slide in the deck there. So that's just for you to summarize. I guess more useful is to remember the picture and the example on the picture. And then you can reconstruct the equation form from there. Now, we've seen how we can use suffix trees to find these longest common extensions using the fact that the lowest common ancestor gives you those. But that's not the same as having an implementation for this LCE problem. If we have the suffix tree, what we could do is just walk up from the two leaves until they meet for the first time. But that could take a long time if these are long suffixes and they don't share a lot of characters at the beginning. You might have to walk up the tree a long while. We could also just pre-compute everything. That's kind of boring. Also takes lots of space. We don't like that. And it takes, if you need that much space, it also takes that much time to fill the table in pre-processing. So that's not great either. We could also, the trivial solution that I didn't even dare to list, we could do no pre-processing at all. That's an E. We could do no pre-processing at all, and just when someone tells you, find me the longest common extension of I and J, you start walking from I and J until they differ. You could do that, but that's slow at query time. So well, more precise, you could say L, where L is the length of this shared prefix. So if you don't expect long shared prefixes, maybe this is not such a crappy solution. But in general, it's not really interesting, and also it doesn't use suffix trees, so we can't be content with that. Now, for the time being, I'll just throw in another magic black box and tell you it is possible to do this. To solve this, well, to compute LCAs, in this case, I've rephrased it in terms of the suffix tree. You can take a suffix tree and pre-process it, spend linear time and space, and afterwards you can find, for any two leaves, their lowest common ancestor in constant time. Boom, you jump there, in worst case, no walking, nothing. Okay? I just copied these bullet points from the suffix tree. It's the same statement. It is a little tricky to understand how this works, but again, it is, we'll completely unwrap this towards the end. And it was a breakthrough when this first was observed, but if you follow the steps in the right way, each little step is quite elementary and easy to follow. It's just combining them all together in the right way took people quite a while. And this will be part of the most practical and useful implementation of suffix trees. So this will not make sense to you at this point. It is useful in practice. Let me just promise this at this stage. So for now, we'll just treat this as a black box. If I give you a text, you can call a magic function, and that in linear time produces you some data structure that in constant time can answer these LCA queries, LCE queries on the string. Okay. So here's the statement for LCE. Here's the statement for LCA. Remember, the two in suffix trees are essentially the same. I put the Matryoshka puppets here because we're starting to use a black box inside a black box. So that's the point where you should get a little uncomfortable if someone promises you that this is practical, but you haven't seen the black box that's now used inside another black box. But I'll get you there eventually. And we'll unwrap the first box soon. All right, I hope you kind of appreciate that this is a cool result. And if you just mess around with simple ideas, it seems you can't get this linear pre-processing time and constant query time for LCE. Same pattern as before. Before we further bother to construct these things, let's see what we can do with this new toy. And there's a lot of different things, but I picked out a few easy to digest examples that are still somewhat cute, I think. The first is, let's depart from the Unit 4 definition of string matching and instead find inexact matches of a pattern. In another way to put it, you're trying to find something in a book, but you slightly mistype the word you're searching. Maybe you want to allow 1 or 2 typos and still find the occurrences. So formally, we're still given a text and still given a pattern, but there's an additional input parameter, a number k. And think usually of k being really small, like 1 or 2 or 3. That's the number of typos you tolerate. And what does tolerate here formally mean? In the simplest version that we'll look at, we want to find occurrences in the text, so substrings of the text, that differ in at most k characters from the pattern. And differ here just means you can replace up to k characters. No deletions or insertions. So if you type in a haste and Google for something, you often omit a character or mistakenly type another one that doesn't belong there. You can handle these things too, but we'll keep things simple for now. So just mismatches. All right. That's something you might have seen elsewhere. It's called the Hamming distance between 2 strings, just the number of positions where they differ. And again, another thing that will pop up later, so I'll throw in this name already. Of course, there's the possibility that the text does not occur any position that is within Hamming distance k of the pattern, so then you just return no match. So it's something like searching with typos in a very simple form. Let's take a quick look at what you can do without any fancy things. If you think back to beginning of Unit 4, our brute force algorithm for string matching. Remember, it just tested one text position after the other, and for each text position, it tried to match the pattern at this point. Now, we can adapt this to that scenario where we don't find exact matches. If we align the pattern at a certain position with the text, we can just ask how many characters are equal, and if there's a mismatch, then we count. And whenever we found a position where there's fewer than k mismatches, we report this as a match. Okay? I didn't prepare code for this, but I think it's conceptually quite simple to do. You could literally take the code from Unit 4 and just include a counter instead of skipping out of the loop right away. So what we're comparing with is this baseline of the brute force string matching. If m is really small, that might be good enough. But if m is not so tiny, this is relatively costly. And remember, for exact string matching, we could easily achieve this time order n plus m. And we were even able to figure out some parallel ways and all these things. So this is much worse, it seems. Now, how does this fit into the section on longest common extensions? Well, let's look at this string where we have the text and the pattern. Again, we applied the same idea as for the generalized suffix trees. Just take the strings, put them, concatenate them, and throw in some dollar symbols. That served us well before. Let's just try the same again. And pre-process this string for the longest common extension queries. So we can do this by building the generalized suffix tree, computing the string depths, and then pre-processing that tree for LCAs. But that's unwrapping the first layer of the black box. You might ignore that part if you want. So we'll try to use LCEs in this one. Before we do that, let's see if you paid attention, and also wake you up again. Just a quick one. You know what to do. It's a simple exercise. It's mainly testing if you remember the definition. The number of emoji has skyrocketed compared to last year. It's definitely, times are changing. There's more smiles in the world again. It's good to see. All right, I'll just show the results. You can still put your vote in, but most people came down to 2 or something close. Thanks, guys. Yep, I guess I provoked that one. So why is it 2? Well, you count. Okay, let me do this on the slides. You keep going. You can see it on your phones. So if you write the 2 words below each other, heart, beard, then there's 3 matches in the middle, but mismatches here. So hamming distance 2. All right. Lovely. Okay. Now, how can we make use of this before I show you the code? So we have this magic toy that tells us in this string, for any 2 positions, how far they continue the same way in the text. How can we make use of that? If we have a position in the text and we have aligned the pattern, we can take this position I and this position j in the text, initially 0, and we can map this to this weird text here, where we have t first, then $1, then the pattern. And well, the position I in the text is still at position I, and this position j is at I plus 1 plus j in this big text. So we can put an LCE query for these 2 positions, and it will tell you in constant time how much you can jump from these 2 positions, and also where the first mismatch is, because it has to come right after. So instead of walking over the green part and having to check all these characters, we can just jump over them. Then we have one character, the red one, where there is a mismatch, so we'll have to deal with that. But then we move over it and jump again. And the trick is we only have to do this k times, because after k, red mismatches, we know it's not a match position. And because of this jumping, people have called this the Kangaroo Algorithm. So this just is code spelling out the idea I just explained. We built the LCE data structure for this combined text, again using the black box inside a black box, and so we'll come back to that eventually. And then we follow the brute force algorithm, but we do jumps. So we test each position in the text. Another time my picture. For each position in the text where we could align the pattern, we count how many mismatches we've already used up. And we keep track of the position inside the pattern. And as long as we have budget for more mismatches and we haven't reached the end of the pattern, we do another jump. And the jump is given by this. So you'll have to decode the formula for the two positions, but I hope didn't make a mistake. So you jump over the matching part. And then there's one mismatch position that you count. And then after that, you jump again. And well, you always increment these by 1 to jump over the mismatch character. If after this loop you found the end of the pattern, that means you didn't run out of mismatch budget before you reached the end. So then you have found a match with up to k mistakes. Then you return this one. Okay? It's a quite simple algorithm, apart from this line. How good is this? The pre-processing will be linear in the size of this text that we generate, and that's the text plus the pattern. So that's length n plus m. And the pre-processing will be linear in that length. That's the part you haven't seen. And then the matching part is this loop. This outer loop runs n times, n minus m, but don't get too Catholic about it. And this inner loop runs at most k times. So we've gone down from n times m to n times k. So this is useful if k is much, much smaller than n. Informally written as much less than m. Not very useful, but shorter than writing it out. So it depends how useful this is. Unfortunately, people have proven that you can't do much, much better. It just seems that these problems where you try to find inexact matches, they're substantially harder than the exact matches. And there are lower bounds that you cannot get around easily. People improved this to more complicated runtimes with much more complicated algorithms. This is like just for your curiosity. This is not the end of the story. But in this model, there's not so easy ways to improve this further. But you should think of k as being relatively small anyways. If you allow many mismatches, you'll find lots of spurious matches in your text. So the useful realm is when k is a small constant. And then this is a really fast algorithm and a huge improvement over the n times m. As a last application for now, is a slight twist on essentially the same problem. We now allow a wildcard character in our pattern. So instead of saying I have a fixed pattern and I want to find inexact matches, I'm now saying I tell you exactly which positions in my pattern. I don't care what character is there. So this is a wildcard in the sense that it can be replaced by any single character. It's not a Unix shell style wildcard where it can be an arbitrary long string. So an example here, the pattern is unit and then star, which could be replaced by unit 5, but it couldn't be replaced by unit 10. It's just a single character. And if you think about it, this is even a slightly easier problem than the one we've just solved. So the Kangaroo algorithm also works for this one. Let me just point out that You can also use suffix trees without using LCEs in that sense. For this specific problem, you can traverse the generalized pattern down the suffix tree. If you have a character, you just go down a path. That's as before for exact matching. And if you have a wildcard, you follow all the child links. So this immediately explodes if you have many wildcards. But if you have few wildcards, it's actually okay. So you would follow sigma to the k paths in the tree when you have k wildcards. So if you just have a few, 1 or 2 or 3, that might be a fine. So the sigma to the k comes from, you traverse the path, now there's a wildcard, which means you don't know what the next character is. It can be anything, so you have to follow all the possible child links. And at most there's sigma, because that's the size of our alphabet. But then you have sigma paths to further go down, so you have to go traverse with all those down. And if there's another wildcard, each of them expands another times into sigma subpaths. So this won't work well if k is reasonably big. But for a very small k, this could be good. And the benefit is that if you have built the suffix tree, you can do this and search the pattern. That's the number of paths we have to walk down. Each path is at most m characters long. So that's how many nodes you have to visit till you found all the potential positions. And then, as before, there's the question, do you want all matches? Then you would have to go to all the leaves below all those paths. Or you just want one, then you jump to the leftmost. So in this case, you can do this inexact matching without having a dependence on the text length. That's the important part I want to point out. Sigma to the k depends only on the pattern. The text can be as long as it wants, as long as you want. The sigma to the k times m doesn't depend on the text size. So this algorithm is in the sense of unit 4. We do some pre-processing of the text, but it is we still do this on the fly. So we're given the text and the pattern, then we do the matching. Whereas this solution is closer to the text indexing flavor. You give the text, pre-processing it once, and then you get several patterns over time. You can think about whether this kind of solution can also work for the previous problem where we didn't know where the k mismatches are. And the answer is yes, but it gets even more expensive. So if k is really, really small, you can still reasonably do it. And yeah, let me leave it with that. There was one thing I didn't point out. That was this one. Again, this is, we don't dive into any details, but if you're worried that this k mismatches is not very realistic, I hinted at this earlier. If you type, then for that application, you often have insertions and deletions of characters. There's a generalized notion called edit distance, which is given 2 strings, what's the minimal number of operations to go from one string to the other? And the operations are replace a character, delete a character, insert a character. And you can generalize these 2 algorithms for edit distance k as opposed to Hamming distance k. But they get a little more tricky, and so I'll skip that here. And so yeah, what I said about this part is also true for Hamming distance, but then it gets even hairier and slower. But it seems that for these inexact matches, that's to some degree inevitable. All right. If you like this kind of stuff, there's a book that has many more applications. I mentioned this before. That was the book I quoted for this statement of Don Knuth. this conjecture, the Bible on suffix trees if you want. But there's more modern sources as well linked on the website. So let me wrap up this part on suffix trees. It's quite clear, at least in hindsight, that this was a threshold invention. It allowed to do things that seemed impossible before, even by experts. And once it was there, it made lots of things relatively easy. It put research level problems into the realm of like exercises for a module like this. Just to wrap up, why is this great? Suffix trees use linear time and space to construct them and to keep them around. And allow to solve all sorts of problems. So they seem somewhat magic. But then once people got used to this in theory, they noticed they're not so great in practice as presented up to now. They're quite fat if you want. They're linear time to construct, but the algorithms that directly construct the suffix tree are quite involved and have quite some overhead. And once you have this tree, you have to represent it somehow in memory. And there's different options. I mentioned this before. You could, for each node, have all child links, all sigma possible child links that uses sigma pointers for each node. So n times sigma if we use an array of pointers. And remember, sigma, it could be ASCII, then it's just 128 or 256. It could be Unicode, then it's 100K times the length of the text. That's not so great. You could bring it down a bit to something like n log sigma if we use dictionaries. But then we can't in constant time go from one node to its children because we have to use a dictionary lookup to get there. So it seems there's no perfect solution, and people played with this quite a while. There's some nice trade-offs, but no one was perfectly happy.